So we'll move on now to a presentation by Leonard Konikow. Leonard Konikow received his BA in geology from Hofstra University and his MS and PhD from Penn State. He started working for the U.S. Geological Survey as a hydrogeologist in 1972, which is exactly the same year that I left the USGS, and is now an emeritus scientist. His research interests include the development and application of simulation models for groundwater flow and contamination problems, groundwater surface water interactions, and groundwater depletion. He is a member of the National Academy of Engineering, fellow of the American Geophysical Union, has received the M.K. Hubbard Award from the NGWA, National Groundwater Association, and the O.E. Meinzer Award from the Geological Society of America. He also served on several committees of the National Research Council and in leadership positions in several professional societies. Lenny?
Thank you, George. I'm going to be talking about the assessment and impacts of long-term groundwater depletion. In the so-called good old days, water wells were few and far between, and pumps were rather primitive, and we did not have to worry about depleting the aquifer. It just wasn't a concern. Today, we have powerful drilling rigs and powerful pumps that can remove vast quantities of water from our groundwater systems. Most of the water withdrawn for groundwater use really goes into irrigated agriculture. And we could see this pretty well in a Landsat image from the area near Garden City, Kansas, which sits on the High Plains Aquifer. Most of these little circles are center pivot irrigation systems. Most of these are a 1/4 mile in diameter, and most of these, if not all of them, are supplied by groundwater. Extensive withdrawals from the underlying aquifer. And where does all this water come from, all this groundwater that's pumped? Well, this was explained by Stavros in his talk, clarified by C.V. Tice in his classic 1940 paper. All groundwater pumpage must be balanced by some combination of a removal of water from storage in the aquifer, which we could call depletion or storage depletion from the groundwater system, plus an increase in recharge or a decrease in discharge, which together can be lumped into a term we call capture. Groundwater depletion can have a number of negative or detrimental environmental effects. We could see one type of effect in Arizona where there was a substantial loss of phreatophytes or vegetation along the Santa Cruz River over this 47-year period. And in this area, water level measurements in wells indicated that the water table has dropped on the order of 100 feet, well below the root zone. Groundwater depletion and declining groundwater levels can affect spring discharge. And we see in this plot a couple of springs in North Africa over the period of much of the 20th century, where spring discharge has decreased dramatically in proportion or in relation to a corresponding increase in groundwater extraction. We can characterize groundwater depletion two ways. One in terms of water level declines, or another in terms of an actual volumetric change in storage. If we look at water level declines, this map from a USGS circular a few years ago, 2008, shows that substantial water level declines and groundwater depletion occurs throughout the United States. It's a pervasive problem, doesn't occur everywhere, but in almost every state we have some evidence that at least in some areas there is substantial groundwater depletion. We could look more specifically, as an example, at a monitoring well in the area of Las Vegas and plot it on the same graph with population growth, and we could see that pretty clearly there seems to be some relation between the increase in population and the decrease in water levels in wells, and this makes sense. Water withdrawals and water use will go up as the population increases. This was pretty consistent through the mid-1990s, and then there was some changes here that as population kept growing, groundwater levels stabilized. And this is attributed to several changes in management policies in that area. They instituted, first of all, some importation of water from the Colorado River, coupled with conservation measures to induce homeowners to get rid of their lawns and stop watering lawns, and other similar measures to reduce water demand and water use. And it clearly had an effect. So we could also look at characterizing groundwater depletion in terms of the change in volume. And one of the things I did was take a look at long-term groundwater depletion in the US and really globally also over the period, the entire 20th century, extended up to the year 2008. And I assessed all the principal aquifers in the United States as well as several international aquifers for which there were data available. And one of the things I did in terms of methodology, I used a variety of methods in trying to assess the actual storage change in these numerous aquifer systems. But basically they were all tied to measurements of change in the individual aquifers. What we found is that in the US, the greatest volumes of depletion, the change in storage, occurred in the High Plains aquifer, shown in red, the Mississippi and Bayman aquifer, with very large changes in the alluvial basins of southern Arizona and the Central Valley of California. What we also saw is that there were actually two large systems in the Pacific Northwest in which there was actually an increase in storage. Groundwater levels are higher today than they were in 1900. There's been an increase in storage. And that's primarily due to the diversion of surface water for flood irrigation, which increased the recharge substantially over what it would have been naturally. We could look at depletion in a non-dimensional sense and relate the depletion volume to the cumulative pumpage to try to get what we would call a depletion fraction and get at where the balance is for the pumpage, for the withdrawals. And what we found for the US, we had sufficient data over this 55-year period to have a reasonably good estimate of what the total withdrawals in the US were, and we had estimates of what the total groundwater depletion was. And it turns out that the groundwater storage depletion was about 15% of the total pumpage, or a depletion fraction of 0.15. And of course that means that 85% of the groundwater pumpage is derived from capture. The depletion fraction in individual aquifer systems varies substantially across the US from aquifer to aquifer, but the trend you could see is that the largest depletion fractions occur in the arid to semi-arid southwestern US, where the potential for increasing recharge or decreasing discharge are the smallest. We could look at the High Plains aquifer, which is Bridget mentioned, and is the single system with the greatest volume of depletion, and because of that is also the best characterized aquifer system in terms of groundwater storage changes. And what we see is that it's a highly non-uniform response with changes in the northern part of the High Plains aquifer being minimal, very few changes in Nebraska, and the most serious problems in Texas and southwestern Kansas, where water level declines are greater than 150 feet since pre-development times. In this aquifer system, the total volume removed from storage through the beginning of 2013 is approaching 400 cubic kilometers. That's about the volume of water in Lake Erie. So we're talking about really large volumes of water. In terms of this aquifer system, we could look at its impact in terms of changes in saturated thickness. Again, minimal damage in the northern end, in Nebraska, in the northern end of the High Plains. And the areas that are red, we have lost more than 50% of the saturated thickness of this aquifer. Most extensively in northern Texas, but also a little bit in Oklahoma and western Kansas, a little bit in Colorado. When you lose half the thickness of the aquifer, you have problems. Clearly, that's not sustainable. We could also look at potential impacts on stream flow, and we'll take one example in southwestern Kansas, and we'll look at the Cimarron River with the gauge right here in the watershed in the area of very high water level declines in the High Plains aquifer. And what we see here in this graph showing changes in storage in the High Plains aquifer, and this showing low flows, 7-day mean annual low flows in the Cimarron River. And what we see is a pretty clear correlation between these two plots. We could also look at an example from the Mississippi embayment aquifer system. Again, primarily agricultural use, a lot of irrigation for rice growing in this area. And what we see, looking at one small watershed in northeastern Arkansas, in an area of heavy groundwater development, we look at the annual mean daily flow in this river. These are the black dots. And what we see is basically no significant trend with time and nothing that parallels the increase in depletion intensity. This is a cumulative depletion intensity curve shown in blue. So these data are highly variable, but no substantial trend in the mean daily flow. But if we look at the annual 7-day low flows in this system, we get a very different picture and a much tighter relationship and a more significant trend with time, with these low flows are decreasing in time as the depletion intensity and drawdowns increase with time. We could also look at the number of zero flow days, and in smaller rivers, under natural conditions, pre-development conditions, you may never have a day when the stream is dry. But when this depletion is kicking in, all of a sudden we have a few days of no flow, and as time increases and depletion increases, we have more and more days in which the stream is dry. So this is another flow characteristic that we could use to characterize the impact of groundwater depletion. In terms of the rates of change of groundwater depletion, we've mapped these out for the U.S., again for the same period, 1900 to 2008. In a few areas, we've updated it to more recent times. And again, the High Plains aquifer is the highest. For the U.S. as a whole, we find that over the 20th century, we accumulated 800 cubic kilometers of depletion over this time period. And what's really a little surprising is that in the next 8 years, the depletion increased 25%. The depletion is actually accelerated. Okay, and this is disconcerting. So if we look at this 20th century depletion, if we take this volume of water that's removed from the continents, figure out, well, where did it go? Ultimately, it winds up in the oceans as the ultimate sink. And if we spread that depletion volume out over the surface area of the oceans, we wind up with 0.2 centimeters of sea level rise. In other words, groundwater depletion in the US in the 20th century can be, is balanced by little more than 1% of the sea level rise. It can explain more than 1% of the sea level rise in the 20th century. Small but non-trivial. But if we look at a global picture, okay, and we've made some assessments of what the global groundwater depletion is. Interesting, we see in the 1990s or so, the total depletion, cumulative depletion in India surpassed that in the United States. Serious problems there. The total global depletion is probably on the order of 4 to 5 times that in the United States. This also will have an even greater impact on sea level rise. And in the 20th century, global groundwater depletion can explain more than 5% of the observed sea level rise. But again, if we look at the more recent data since the year 2000, what we find is that in these recent years, the rate of sea level rise has actually increased from the 20th century average of about 1.8 millimeters per year. But groundwater depletion globally has increased even more. So that during this last decade of this study, groundwater depletion can actually explain 12 to 13% of the observed sea level rise. This is getting to magnitudes that really need to be accounted for by those dealing with sea level rise. So this is an example of a global impact of groundwater depletion. So what does the future hold? Well, that's always an interesting question. One thing I think most people will agree is that the population continues to grow, and that this population growth is a driving force for increased demands for food and water supply. So things are going to get more stressed in the future in terms of water. We could also agree, most of us will agree, climate is changing and hydrologic systems are changing, partly due to climate change, partly due to other anthropogenic forces. So because of these factors, we will need both improved water management, which will help but may not solve all the problems. So we will also need to adapt to these changes one way or another. So what are our management and policy options? Well, one is we can be passive about it. What this might imply is that we basically have to accept groundwater depletion and accept that it is ultimately a self-limiting process. Okay, and what that means, if we don't do anything about it, it will take care of itself. We will not like the consequences, though. Or we could take a more active management and policy approach, and these really need to be linked with technology advances and with innovative engineering solutions. As Bridget explained, this boils down to two categories. We could strive to decrease water use, decrease demand. This will be most fruitful in dealing with irrigated agriculture, and there are a number of options there. Or we could increase supply, and there are a number of ways that we could do that. And again, most of these will involve innovative engineering solutions. So, in conclusion, it's clear that most groundwater withdrawals are balanced by capture, much less by storage depletion, and yet, in spite of this, groundwater depletion is continuing to grow, if not accelerate, at this time. So what I would also conclude is that better and more monitoring and assessment of groundwater depletion is needed, and at least needs to be keyed to observation and understanding of the individual aquifer systems itself. Depletion causes a number of detrimental environmental effects, and I think it's clear that streamflow depletion is related to and can be caused by groundwater depletion, at least in some cases. The long-term implication is that groundwater depletion can affect the sustainability of water supplies, but innovative water management actions can indeed help mitigate these problems. Thank you.
We have questions for Lenny?
Excellent talk.
Thank you.
As a non-expert in this area, I learned a lot. Thank you. My question is about sea level rise. So are you assuming that all of the depletion goes into the sea to cause a sea level rise?
Well, it's not the only cause of sea level. It's not even the major source of sea
Yeah.
level rise.
But
The assumption in that analysis is that when an aquifer is depleted, such as the High Plains aquifer, where is all that water going? Where does it wind up? Well, some of it goes on the land surface, it goes in the soil moisture. Most of it is evapotranspired,
yeah.
wind up in the atmosphere, but the residence time in the atmosphere is very short relative to groundwater flow and transport times. It gets in the atmosphere, or it flows overland, winds up in rivers. The ultimate sink for the great majority of this water is the ocean.
So
That's
in
where
your
it winds up with the longest residence time. And there have been studies estimating this. I've seen various numbers that it's 97% and
Okay.
various others. But you know that for that estimate, I just first approximation assume it all winds up in the
Okay.
ocean
Thank you.
eventually.
Doesn't also depletion of the groundwater reduce the groundwater discharge into the oceans, which will cause a reverse effect?
Okay, sorry, Stavros.
There are many aquifers which discharge in into the sea. We got springs in oceans. And the coastal plain, when we got the recharge areas, eventually the water discharges into the ocean. Now when you're depleting it, you are reducing the discharge to the ocean. So that would then have a counter effect to the increased precipitation because of the...
Can you repeat the question?
Okay, I'm not sure I got the whole question.
I
but
got the whole question. Here's the whole question.
No,
Lenny is arguing that there's an increase in the amount of water that goes to the sea from this process. Stavros says, well, groundwater normally discharges to the ocean, and with this decrease in the water level in the groundwater, there should be less flow to the ocean. Aren't these countermeasures?
Yes, and the answer to that is yes. There would be, in coastal aquifers with extensive groundwater pumpage, there would be less discharge to the oceans, to streams, or to wherever. That's the balance that we all know and believe in. This induces seawater intrusion, okay, as part of the balance, but what I'm looking at, even in the coastal aquifers, is what the net change in the volume of water stored in that aquifer is. So, you know, you look at any of these coastal aquifers, you could have large cones of depression which reflect whatever period of time you look at, there's a net change in storage in that system. In a coastal aquifer, it's certainly recoverable more quickly than in a high plains aquifer. And we don't look at whether that replacement is freshwater or saltwater. We're just looking at a volumetric change.
So I would like to also thank you for this excellent presentation. And I appreciate that you mentioned that population pressure on groundwater and other demographic and economic factors. So my question actually links to the previous presentation, and you showed different models that have a large variability in their projections. And my question is, what's the benefit of these models in terms of projecting the future, and how many of these models integrate these demographic and economic factors in the future projections?
Well, I think
Both the speakers could respond.
I'll take that. I'll give you my view first, and then Bridget, or we could save that for the panel discussion. But basically, most of these models get pretty weak when you project into the future. A lot of the land surface models, global scale models that Bridget was talking about have really very, very coarse assumptions in them. Most of them do not recognize or deal with anything about groundwater hydraulics or the dynamics of the systems. They're really looking at groundwater as a big box. What I'm trying to do in most of my assessments is look closer at the individual systems, okay? But again, projection into the future is really, really sketchy, except we know if we continue to operate the way we've been operating, water levels are going to continue to go down, and we're going to get into more and more trouble. And, you know, there's a number of things that will happen. There's a number of things we could do. Some states are at least beginning to recognize this issue. Arizona in I think it was around 1980, passed a whole new set of laws because of their groundwater depletion problem, and this has had a beneficial effect. It hasn't completely solved the problem, but it has helped a lot. In 2014, California finally passed some laws that will help it manage groundwater depletion.
Thank you, Lenny.
Add anything, Bridget? No.
Thanks, Lenny. So our